Okay, good afternoon and welcome to this session of Math Chats. Just want to put a note out there that this opportunity is being made available to you through a combination of a partnership between DPI and your North Dakota REAs. Our goal is really just to get some messages out there so we can work on improving student math achievement in North Dakota. This is being recorded so that we can put it online on the hub for asynchronous viewing. Just a quick introduction to who I am. I am an instructional coach that worked with Bismarck Public Schools for many years, both as their math coach and general instructional coach. When I retired a few years ago, the goal was to focus on math instruction. And so we have this opportunity to do it statewide. So I am very glad for any of you that can make it here. For the most part, it is people that are working with us throughout North Dakota on the Math Chat. We're going to have a Q&A all the way through. If you have a question, just enter it in the chat if that's more comfortable. There are lots of people here that will be monitoring it. But if you prefer, you can just turn the mic on. This is very informal, and ask your question or raise your hand at the bottom of your screen, your virtual hand, and we will check on what it is you're doing. Okay, as several of us are preparing to do this work throughout the state, we have been reading and going through what would be considered our research-based instruction, not just what it looks like in math, but what it looks like in other areas, to make sure we are giving you the most up-to-date information on any of the strategies that we're talking about. Some of you might be familiar with Project Follow-Through, but if you've never heard of Project Follow-Through, it was started in 1967 and ran for several decades. It cost the United States millions of dollars, and its whole point was to pit 24 different instructional programs against each other to see which one came out on top. These programs were divided into the three categories that you see on the screen: the basic skills model, conceptual models, and affective cognitive models. Were they positive about math? Did they think they could do math? All of the children that were part of the study took the assessment in each of the different areas. So there were 3 different assessments, and no matter which group they were in, they took all 3 of the assessments. When I think about this, I think about the capital DI. One of the programs was called Direct Instruction, and it was one of the basic skills models that were tested. But there were 3 different models in each of the area. Where you see the arrow pointing at the 0, there were a number of students that did not participate in any of the programs. They received instruction as normal from their classroom's teacher in their school. The 0 represents all of those kids that did not participate in the study. That 0 represents the average score of all of those students. The basic skills group are the dark black, the cognitive are the lighter gray, and the ones in the affective group are white. It shows how their scores compared in all of these three levels, depending on which program they participated in. If you notice, on the very first one is the direct instruction one, and it shows growth in all 3 different areas. And some, they didn't show growth in any of the other areas. And the bottom line is, for some of them, they actually showed negative growth, okay? And so that really tells us what the direct instruction looks like. There is a difference that I found out between the capital DI and the lower DI. The capital DI refers specifically to the program that was developed at this time for direct instruction, and the lowercase DI refers to the instructional strategies that were used within it, right? What we usually see is just the lowercase DI, and the direct instruction and what it looks like now in education. And it's often confused with something that has to be written from a script, but that's not necessarily the case at all, although there are programs that use direct instruction that are written from a script. I want to take a look at the effect size of what we're going to talk about today, but also a few of the strategies that are used throughout different programs and different content areas. I want you to take just a quick glance at what those effect size of different things are. Our North Dakota math scores last year, 39% of our kids were proficient. As we go from district to district, there are a few of them that have it higher than that. There are a lot of them slightly lower, but we're sitting at 39% as a state. And I know we would all like to see that go up. Normally in a virtual workshop, I would not have you listen to a video, but in order for us to understand what it means, I want to show a video that does a much better job explaining effect size in simpler form than for us to explain it mathematically.
Here we have a student. Let's name him John. John is in a class of 25 people. He's an average student, which means that he is number 13 on all of his assignments. One day, a researcher sitting in her office has an idea. She has just thought of a great intervention for students, but she needs to test this idea. So, she approaches John's school and gets permission to perform an experiment using two classes, John's and one other in the same grade. To measure the impact of the intervention, the researcher gives a pretest to get a baseline. When she analyzes the results, she sees that the two classes are just about equal. This means that John, the average student in his class, receives just about the same grade as the average student in the other class. So the researcher decides to give John's class the intervention she has thought of and does nothing with the second class, so that they are the control. Then the researcher gives a post-test to see how well the intervention worked. If it did not work, she expects John to still be equal with the average student in the other class. But when she analyzes the data, she finds that they are not equal, that, in fact, John's class has improved a lot. The researcher then calculates the effect size for the intervention, or how well the intervention worked, and finds that the effect size for her intervention was 1.7. But what exactly does this mean? Well, if we look at our two classes again, and we remember that John was the average student, we will see what different effect sizes mean for him. For an effect of 0, if we took John out of his class and moved him to the class that did not receive the intervention, he would still be average, number 13. This means that nothing changed. The intervention had no effect. But if we saw an effect of 0.3 and we took John from his class after the intervention and moved him to the other class, he would now be number 10. He is now performing better than a majority of students in the class on the post-test. But what happens with even larger effect sizes? An effect of 0.8 would mean that John, if he were transferred to the class that did not get the intervention, would be 6th. An effect size of 1.6 is even greater. He would now place 1st in the class that did not receive the intervention. An effect size of 2 means that we could take John from his class and place him in a group of 44 peers that did not receive the intervention, and he would still be on top of that group. And the most extreme example we have, an effect size of 3. If John, remember John is an average student in his class, if he were moved to a group of 740 students who did not receive the intervention, he would be on the top of that group. Basically, if we moved him to an elementary school that was equal to his previous school in demographics and performance, but that had never received the intervention, he would be the top of the school, and he was average in his class, and we can assume in his school. This is an extremely effective intervention. So, where does that leave our researcher from before? Remember, the effect size of her intervention was 1.7. So, the average student, John, from the experimental class, the one that received the intervention, would be in the top of the control class, the one that did not receive the intervention, if he were moved there afterwards. So, we can say there was a large effect. In summary, effect sizes tell us how much impact an intervention had. Remember, we want to see an effect size of at least 0.3 to say it was effective. Thanks for watching. Feel free to contact me for more information on this topic.
Let's look back at the effect sizes that were in our table. This table tells us what we should and what we shouldn't do while we're teaching a new skill in math. These instructional strategies that are listed on the bottom, they're viable strategies in certain content areas. And even if we're talking about once a student has learned a skill and we want them to apply the skill, but take a look at what these highest effect sizes occur in. Explicit instruction. And that is our goal today. The only thing I've seen with a higher effect size is teacher efficacy, our ability to work together. That has an effect size of 1.57. So if we can start applying these and work together, we will get our North Dakota scores to grow. One of the books that I looked at is called The New Classroom Instruction That Works. Within that book, it gave 6 different learning phases and what occurs in each of those phases. What I want to take a look at quickly is the 3rd phase, focus on new learning. Once we have students interested, we get them engaged in their learning. These are the 3 strategies that we should be using in mathematics at that time: vocabulary instruction, strategy and modeling, and visualizations and concrete examples, all of which are part of explicit instruction. Different authors and different researchers, they organize the information from the research differently, but the main points of information is still the same. Patton Mathematics in Pennsylvania, they organize theirs into what they call an instructional hierarchy. And what we're going to do this afternoon is to take a look at this first stage, the acquisition stage. The acquisition stage, it's when they're learning a new skill. They're still slow and inaccurate. They are working on learning the skill. At this point, we should provide direct and explicit instruction that includes a lot of demonstration, a lot of guided practicing, a lot of modeling from the teacher. We have to be able to give immediate feedback, specific feedback. You might use modeling of concrete objects. That really helps us, especially with the struggling kids at the acquisition stage. This table shows what the different stages within the acquisition stage are, or within the instructional hierarchy are. As we look at this first stage, we can see that the students' errors are going to continue to come down and come down. We want them to be pretty accurate before we start working on proficiency and before we give them those generalization and adaptation problems. We know they mastered it when they can apply it. But when we're in the acquisition stage, we're really talking the importance of instruction. So we should be restricting the task and how much we're giving information. Make sure we're giving them immediate feedback so we can correct those mistakes before they become habits, and eventually move to more elaborate feedback, specific feedback on the whole progress of that they're making towards becoming fluent. When we look at the effect sizes on the left, this is what strategies are included in what we call the gradual release model. We may call it I do, we do, you do. We may call it teacher instruction first, student practice, then independent practice. But if you look at the effect size, the video told us that anything over 0.3, 0.3, we were getting a good effect size. Everything within this has 0.58 and higher. So this first one is what we're going to focus on today. Explicitly teach and model the skills. Remain in this phase until you see they are ready to move to the next phase on formative data. Before we are doing too much guided practice with the students, we want to make sure we have given them several examples and they are ready to move. We can consider in the acquisition stage, we're going to start with explicit modeling, and explicit modeling may occur all the way through this, even when we start guided practice. Guided practice occurs between acquisition and fluency before we let them go on their own for independent practice. I really thought this quote fit our goals for today. You don't understand anything until you've learned it in more than one way. And that's what our goal is. If our kids are truly proficient, they can do it more than one way. Explicit systematic instruction, we often just say explicit instruction, but it involves teaching this concept in a highly structured, carefully sequenced manner. Research shows us that this is the best way to teach mathematics and can improve a student's ability to perform any of our operations, adding, multiplying, finding the square. Explicit instruction is not limited to just our K through 3 classrooms. It should be happening in our K through, I would say 16 classrooms, right? Any of you take it from a college instructor where you had no idea what they were talking about? Me, maybe more than once. So let's look at exactly what does it mean to be explicit teacher modeling. We're providing the students with very clear example of the skill. So the teacher describes and models the skill or concept first. They describe the features that they're performing. They do it in learnable sequence and chunks. If it's possible to use multisensory techniques, and especially in the early grades, you should be digging out those manipulatives or showing them representations on the document camera or on the virtual board in front of you. Teacher engages students through demonstrating enthusiasm. Maintain a lively pace. Don't sit and wait for them. If we go too slowly, we start to lose them. And if any of you taught middle school, if you give them a void, they will fill it. That behavior that we don't want to see, that's what we're going to get. Ask the student questions. Check for student understandings. I often hear the complaint, but this is too teacher-centered and not student-centered. If it's too teacher-centered, that's on us, because we should be modeling. We should be checking for understanding. We should be having them show and do examples with us and do examples on their own so that we can give immediate feedback. When we are doing the instruction, it's essential that we break it down into critical features. Think aloud, talk aloud, model out loud. The teacher should describe what she does in every step and why she's doing it or he's doing it. Model examples, but not just examples, non-examples. We learn naturally. Behavior psychology says we learn not to do things when they're painful, uncomfortable, or wrong. Same thing in math. If we're showing them non-examples and why it doesn't work, it helps them understand the correct examples better. Cueing, and this is one of the ones that I model most in classrooms. It's not natural to cue when the kid should be working, when the kid should be doing things, but it really helps to organize and give them hints on what it is they should be doing. When we're doing explicit instruction and we're doing it well, we have high levels of student interaction. The students are participating, they're answering questions, they have the whiteboards out. They're correcting their mistakes, and we're moving from one activity to the next. Explicit instruction is most effective when we do two things with it. One is that we need to hook on to what they already know. So when we start out, we're sure they're going to be successful. We want to get them engaged, and we want to set the stage for learning for that next area. But as important, and maybe more important, is how we scaffold the instruction. We want to make sure that we do it in chunks and we give them feedback before we go to the next chunk. We want to make sure that we provide that initial learning, any additional instruction they need to before we go to the next step or they go to the next step. Too often in classrooms, we cover material. We don't give them enough time to practice the material and what that looks like. One of my favorite examples that I got through the reading is what this high school teacher calls slow motion math problems. And the title of the book is Explicit Instruction, and it was just recently came out in 2021. But what he talks about is after demonstrating a worked example, he would ask the students to show them the same thing and do the 4-step problem on their whiteboards. But when he sat down with his PLC, with his teaching partner, her kids had performed way better on the assessment than his kids did. And as they talked, they figured out that the reason why is these last few things on the bottom. She asked the students to perform just the first step of their problems on the mini whiteboard and hold it aloft so they could see if they were ready to go to the next step. Then they could give them feedback. Then they were allowed to do the next step. And then she would give them feedback. And she continued this process through many problems. In kindergarten, young children can only focus their attention on 2 or 3 things at one time. Well, this little young lady was 4 when she did this, and her mom told her what? You can't go outside without your jacket, your cap, and your mittens. Well, she had those when she went outside to find mom, right? If we aren't considering and breaking things down, they can only hold on to 2 to 3 things at a time. Surprisingly, adults can't do more than 3 or 4. So when we're working with any of those problems that are multi-step problems in that learning phase, that acquisition phase, it's important for us to think about how we can do slow motion problems and give them feedback after every step of the problem before they move on. Within explicit systematic instruction, these are the things that we can do to create a better learning experience for our students. We can regulate the task complexity. When teaching a lesson, start with the simple tasks and move to the tasks that are more complex. Do the same even within every section of the lesson, not just the beginning. Start off slow, build to the next task, and the next task. Eventually, the students will be doing all the steps. But don't model the entire problem first and model 2 or 3 and then set them loose to do the whole thing on their own. Once you've modeled to 2 or 3 problems, you work through them a little at a time and check that they're doing each step okay. Try to anticipate any potential difficulties that there might be. When you're considering any of the misconceptions that your students may get from the material, you can sequence your tasks accordingly. Sequence that instruction then. You want to focus on your instructional focus, communicate to the students in a clear and concise manner. You want to keep up a lively pace. Make sure that what you're teaching overlaps as you're working through it. Create routines, create procedures. The more consistent your routines, transitions, the high expectations are, the better your students are going to live up to those things. And they will increase their learning naturally, just like our effect sizes show. What is math proficiency? Although this isn't defined quite as clearly as it is in reading, there are several areas that have been identified specifically of what we consider math proficiency. The understanding of concepts and operations and how they relate, being able to use procedures flexibly, accurately, efficiently. It doesn't say algorithm. There's more to it than that, but they need to be able to do that efficiently. The most recent psychology behavioral science tells us that if students are working on the simpler tasks and trying to figure them out when you're asking them to do a higher level task, their brains can't keep up. They can't do all those things at one time. Strategies, we want them to be able to represent what the problem looks like, to formulate a plan to solve it. They should be able to reflect on what they're doing, justify what they did, and explain it. We also need them to see math as sensible, and that it's worthwhile. We can't go through a day without math. But how many times do we hear a student or a parent tell us, well, I'm not good at math, so my student or my child probably isn't going to be good at math. One of the biggest misconceptions that's out there, and one of the biggest things that I get asked about, is which should come first, conceptual or procedural understanding? And we've been told for many years that conceptual understanding should come first, and once we do that, we can build a procedural on top of it. But the bottom line is that they support each other. They should be taught together. For some of us, that procedural knowledge is going to make more sense and we can apply it to the conceptual. Or when we're doing the conceptual by the procedural, they explain each other. It's a two-way street. They need to be done together. It's difficult to measure independently which one is working better than the other. However, we do know that when they're taught together, that the understanding and the information is held on longer and the students understand it better than whether we do concepts, then procedures, or procedures, then concepts. When we intertwine them together, it is much easier for students to retain and understand the information. So what does that mean? That when we're teaching these, we have to remember that procedures include more than algorithms, but we do have to have an expectation that they're going to have an efficient and effective method to do it. And we have to understand that being able to do these things more effectively is going to lead to better problem-solving procedures and skills in the next step. What does it look like when we model conceptual and procedural instruction together? Well, think of it as interleaving them as you go through the problem. We're going to watch this one, a couple short videos that give you a demonstration of what does that look like when we do them together.
Today, we are learning how to subtract. This problem is asking us to solve 6 minus 3. We can start with 6, 1, 2, 3, 4, 5, 6. Then take away 3, 1, 2, 3, and then count how many are left. 1, 2, 3. And this gives us our answer. The difference between 6 and 3 is 3. We can also see this easily on a number line. We can start with 6, then count back 3 units, 5, 4, 3, and this also tells us that 6 minus 3 equals 3, or the difference between 6 and 3 is 3. There is an easier way to solve subtraction problems, however. When we solve 6 minus 3, this is the same as asking us how much must we add to 3 to get to 6. So we can start with 3, then count up 4, 5, 6, and that will give us our answer. 3 plus 3 equals 6. Therefore, 6 minus 3 equals 3.
That's something to remember and realize, whether we're talking about addition or subtraction or multiplication and division, is that we do need to relate them together. And research shows us that children understand subtraction better if we teach it at the same time we're teaching addition. At the same time we're teaching multiplication, we can demonstrate division. Same type of situation. That first one was a very K through 3 problem. This one shows you an example of what that would look like with modeling. Pay attention how she's thinking aloud every step that she's doing, but that she's capturing it both procedurally, that equation, besides the modeling conceptual understanding that we see her drawing.
Today we are learning how to multiply with hundreds, tens, and ones. This problem is asking us to solve 121 times 3. Let me show you how. Step 1, we will multiply the ones. We have 3 ones we will multiply times 1 1, which will give us 3 ones, and we record that in our ones position. Next, we will multiply the tens. So we will multiply 3 times 2 tens for 6 tens and record that here in the tens position. Step 3, we will multiply our hundreds. So we have 3 ones times 100, which we will record as 300s here. And that gives us our final product of 363. Now, we could also think about this problem this way. We can think of 121 as 100 plus 20 plus 1, and then think of our 3 ones as 3 ones. Then we multiply 3 times 100 gives us 300, plus 3 times 20 gives us 60, plus 3 times 1 gives us 3. And then when we add our hundreds, tens, and ones back together, we will have a final product of 363. We could also imagine this on a number line. When we are solving 3 times 121, we are really solving for 3 sets of 121. We could count to get to 363. That would take forever, but we could also add. And if we added, we would have 1 set of 121 2 sets of 121 equals 242, and 3 sets of 121 equals 363. Because remember, multiplication is really always just repeated addition, no matter what size the factor is that we are working with. Okay, let's take one that looks like this. Now we are working with 57 times 3. Again, we could add 57 3 times and it would take us to a correct final product, or we can simply multiply, which will be faster and easier. The steps are the same. So step 1, we will multiply the ones. Here we have 3 times 7 ones, which we will record here as 21 ones. We cannot record 21 ones in our final answer this way. So step 2, we must make tens. We can think of 21 as 20 plus 1 when we take the tens out, and we can move the 2 tens or 20 to our tens column to add to our final product. Now we have 1 remaining in our ones position. Okay, now we must multiply our tens and then add the tens that we had to make from the 21. And we do that like so. 5 tens times 3 is 150 plus 20 that we had to make when we took 20 from 21. That will give us 17 tens or 170, which we record like this. And we have our final product of 171. Now, we could also think about this problem this way. We can think of 57 as being 50 plus 7. We can think of 3 ones as being 3 ones. And then we just multiply. 3 ones times 50 gives us 150, plus 3 times 7 gives us 21. And then we add those hundreds and tens quantities together, and we have our final correct product of 171. If we mapped this on the number line, we would count 1 set of 57, 2 sets of 57, and 3 sets of 57 would take us to our correct final product of 171.
One thing I would really strongly suggest is that if you haven't taught addition, multiplication on the number line before, that you practice a little bit, because it is one of the most successful ways for student to understand addition, subtraction, multiplication, and division is through a number line. And so if we can show that confidently and demonstrate that, and there's all kinds of interactive number lines out on the web, that we can really help to improve their understanding. And we'll look at the IES practice guide here at the end, and that is one of the things that they really encourage us to start thinking about how we could do that. There's one more thing to consider when you think about modeling math, and that's that there's a lot of support for what we call the concrete representational abstract modeling framework. Some call it concrete pictorial abstract. You'll see CPA, CRA in different textbooks in different places. And it talks about the concrete to representational to abstract. And math learning goes through this sequence pretty much at all levels. Our higher kiddos can understand the abstract without either of these coming before it. But for about 70% of our students, it's important that they can see and understand these things. One of the mistakes we make a mistake with when we want the kids to get the abstract is we show them the concrete, then we put it away. And then we show them the visual and we put it away. And then we show them the abstract that we expect them to get from what we already taught them. But we don't show all 3 of them at the same time. One thing that we have to have, and we don't have to show all 3. We could do concrete next to abstract. We could do visual next to abstract. But when we show the abstract version first, we should have one of these beside it. And when we show the concrete and visual, we should have the equation beside it. So they start making that connection right away, that they're not different things. They're the same thing and what they look like together. Let's go back and take just a quick look at some of the main instructional elements within modeling. and explicit instruction. We talked about the teacher modeling and how we have to think aloud. It's not just teacher. There has to be a lot of active participation from the students. The examples we just looked at would be the student or the teacher examples at the beginning, the I do, but then we would work into the we do together as we work through problems step by step, asking these questions. Multiple examples. Most of our textbooks do not have enough examples for the teacher. We should be modeling at the minimum 2 or 3 before we move into guided instruction. Doing it in multiple grouping formats, whole group, small group, paired up, all of those things provide us with extra opportunities to respond, as well as getting feedback from each other and what we're doing. It really, really helps. Manipulatives, visual cues, all of those can lead our students to better understanding. There are a few states that have been working on this a little bit longer than North Dakota. This video comes from Pennsylvania, and they have been doing a lot of work in this area. It covers all the different things that we have been talking about, but I'm not going to make you watch another video. But I do want to remind you that in the hub where you download the materials for this math chat and for any of the other ones, the PDFs that are in there are interactive. So any of the links that I have in the slideshows that I'm showing you, or if you were to go back and watch some of the other ones, they are linked and interactive, and you would be able to go and get a little more information. We want to make sure we talk about scaffolding, though. It's one of the best things that we can do when we're teaching kids, but it's also can be one of the worst things we do if we don't take it away. Scaffolding means that we want them to progress eventually, so we're not needed, and they can do it independently. But independently means without any of the scaffolding that we provided along the way. As we're working through these elements of explicit instruction, we're going to do guided practice. We're going to sequence examples, but eventually we're going to take away those things. So let's think about an example that is probably very familiar to all of us, and that's learning to ride a bike. Okay, so in this real life example, imagine that the father is teaching his daughter how to ride a bike. He would not begin by placing her on the bike, letting go, and say, "Good luck." It would be much more effective to first introduce the girl to the bike, explain what it can do, what the different parts of the bike are. He could put her on the seat and hold onto it while she gets a feel for it. Next, he could help her understand how to pedal and steer, all while he's holding her upright. And as she does that, she's going to move from one rung to the next until she can be successful. So let's think about that a little bit. First, what we would do, our goal is that she's going to learn to ride the bike, right? So odds are I probably put training wheels on it when I had her come familiar with the bike. I put those training wheels on so that she would be safe and she would feel successful even though she couldn't ride it independently yet. I'm going to let her ride the bike with those training wheels on for a little while. Eventually, I'm going to take it off. I'm going to hold the seat as she rides. I'm going to give her pointers. I'm going to help her understand balance. And then I'm going to remove those supports that I gave her. So the last thing, she's going to practice riding the bike so we can remove those training wheels. And that's one of the important things we have to remember in math is if it's scaffolding, we do these things along the way, but the students have to know and understand, and we have to make sure to share with them what the scaffoldings are that we're giving them now, but that we're going to take away in the end. They will be much more successful as we guide them through it, but they need to know they will come away in the end. So there's a lot of scaffolding that occurs naturally within explicit instruction that we don't even have to plan for. We just have to know it occurs. When we break that task into smaller parts and teach it piece by piece by piece, we're providing scaffolding. As I'm thinking aloud and verbalizing the task and what it looks like, I'm providing scaffolding. The different types of format, when they work in cooperative learning, they work in their team, it provides scaffolding. One of the things that we don't do with this one sometimes is we don't make sure they can do it independently if we've allowed them to learn how to do it with a group, okay? Our goal is independence. We might provide prompting, questioning, coaching, all of these things along the way, making sure that we activate background knowledge so that they feel successful, give tips, give strategies, all those things. But the I do, we do, you do means that last part, the goal for everyone, for every kiddo, is to remove any of those scaffoldings that we gave them along the way. So as we think about back to the gradual release model, I want to look at these next couple steps that happen. Provide guided practice with students, targeted immediate feedback, lots of it. Gradually release responsibility to students as they demonstrate mastery. Here is the clicker. Remain in this phase until you see they are ready to move to the next phase based on formative data. We know that's not always possible, right? And it's not always possible with every single standard that we have. So we have to look at our North Dakota standards. Some of you work in districts where they have identified the priority standards for your district. If you do not have them identified within your district, you can go to the North Dakota REA site and it will lead you to the North Dakota standards-based learning site. And North Dakota teachers and others have worked together to identify those priority standards. The priority standards is what we have to follow this gradual release teaching model for. We want to make sure if the next grade level depends on our students' ability to do that standards, we have to know that we can lead them there. We need to keep them in the phase till they're ready to go. We can do this with 6 to 9 standards, not with 26 standards. Practice makes perfect. If they're practicing incorrectly, we're not going to get them on the right track. The more targeted feedback, the more practice you can give them. Once we do this, they are ready to apply and generalize that understanding to more difficult word problems, to problem-based learning activities, to inquiry and constructivism type activities. They will be successful and everyone will have success and they will be able to have more success at the next grade level. Couple things I want to cover before we get done, and there's a few more slides, so don't sneak out on me yet. We do have to think about planning, and sometimes this planning is within our book and it's done there, they already have it, but we have to know what to look for when we look through our book and what does it look like. Modeling with the teacher, think aloud, that's something we need to practice. Taking the time to check for understanding, that's our formative assessment. Ensuring participation through application, get those whiteboards out, get the students practicing, get them through some of those story problems and adaptation problems that fall at the end. Diminish your prompts and models as they progress. Don't forget to take away any of the scaffolding that you provide them. Explicit instruction is very much integrated with all of the other things as teachers we are asked to do, and will actually make a lot of those things easier. If we know what we're planning, we're not developing a whole bunch of different things. We're just breaking what we have to do down into smaller pieces. Formative assessment is very much built into it. We're using the data that we are looking at both in paper form and our observations. Our grouping can be determined based on, I want to teach that skill until 80% of my kids have it. If we're really going to get to 80% of our kids being proficient, we have got to know that 80% of our kids can do it. Then those handful of kids that are not in that 80%, I know they're the ones that I need to pull back to my kidney table in the back. I need to get more small group instruction going with them. My pacing, it defines what my pacing looks like. And the more I use explicit instruction and I'm able to keep going at a livelier pace, the more problems my kids are going to get done in a day. That differentiation with the scaffolding is provided. Classroom management, we know that if they are allowed to have a break, right? We said it before. If there's a void, they will fill it. Using explicit instruction really keeps our kids on task. It keeps them busy and active in what we're doing, and they're less likely to find something to do on their own. Motivation will be higher. The more successful, success builds motivation. The more successful our students can be, the more motivated they will be to work with us. I mentioned about looking through your teacher's manual. Some of you might not have a teacher's manual. You might have teacher developed resources. You might have open resources you get off the web. You need to look through them. What does it provide you with to help you practice those prerequisite skills that we talked about? We want to start with what they know and are able to do at the beginning. How well does it define that explicit instruction sequence for you so that you can follow it with your students as you are working? If you're using any of your teacher-made units, your open resources, you just have to know what these things are. In your book, you have to know what strengths and what weaknesses are within that book so that you can make those adjustments yourself. Does it provide math models? Are the models just for teacher-led, but are they also teacher-led and student use? Does it use number lines or 10 frames? The CRA approach that we talked about. How does your book or your resource help you to understand how to model the math? If you have a textbook that you use in multiple grade levels, they often use the same type of models. If you're choosing what way to model it on your own, then it's important that you talk to the grade level above and below you so that you can tie those models together. Math vocabulary. We know that a lot of the reason our kids can't do story problems is they can't read the story problems. Math is a vocabulary in and of itself. It's important that you think about how you can explicitly teach that vocabulary the same way you teach any other content in math. How can you explicitly teach it and practice it? There should be a number of instructional examples for you as the teacher. Okay, and you want those examples to be at least as complex as the students are going to practice. We shouldn't be expecting them to get through harder and harder problems towards the end of his assignment when they haven't participated or seen any of those examples similar to it being worked out. Is there enough practice problems so you can go through that gradual release model? If not, in the lower grades, it's pretty simple to make up problems on the fly. If not, we can look at those extra practice worksheets that they give us or extra practice problems in our book and find a few problems that we can work with the students as I'm modeling, as they're working, and have more problems for them to go through. Ability is of little account without opportunity. If we're not giving them more opportunities to practice, more opportunities to learn, we're not going to get what we want to see, which is improvement. One of the last things I want to take you back to is that idea of acquisition. That very beginning, when you have a novice learner, when you're having a learner up in the upper grades that has never seen a skill before, it is so important that we provide the explicit instruction, the feedback during this level before we move to their practicing for fluency, okay? Our fluency is not going to come unless they're able to solve the problems accurately. Even if it takes some time, we're okay with that. Consider for those kids that are struggling, what are we going to do? There's 5 more explicit systematic instruction, whether it's in small group, whether it's with Title I, whether it's with you, more modeling, more examples that you show and work with them, simply more practice, more feedback, and more time. And that's our preps right here, right? There's only so much time. So always think about that. You're really going to focus on the systematic explicit instruction when you're teaching your priority standards, when you know that they're going to need this skill before you can move to the next skill. How can we find time to do those standards and not everything that's there? There's 3 different places I would really encourage you to go and look to get a little bit more information on what does best practice teaching look like. We're going to take 2 minutes and look at the Institute of Educational Science, What Works Clearinghouse, and what they show us that they have put together the data on for what works in education, the National Center of Intensive Intervention, and then we looked a little bit at the science of math earlier. All of these links are within here that you could open up if you are so inclined, or the websites are listed below. But let's take a look at here. The Institute of Educational Science identified very recently, March of 2021, they put out this practice guide in your elementary grades K through 8, and a lot of these things apply higher. All 6 of them have strong evidence that they will work if we apply them in our classrooms. They're all tier 1 interventions. We have to consider that intervention applies to most of our students when we only have 40% of them proficient. So what are class-wide interventions we should be doing? This first one is systematic instruction, exactly what we've been talking about. Teaching mathematical language, representations that procedural and conceptual together. Number 4, I mentioned this one earlier briefly, but number lines have been proven to be one of the best ways to help them build understanding in grade level material and to help them be able to apply that in later mathematics. If you have a lot of trouble with your kids with word problems, helping to give deliberate systematic instruction in word problems has shown to improve. And the last one is looking at timed activities. The link for the practice guide is down here on the right. When you go there, you can hit show more, and it literally tells us how we can carry out those things within our classrooms. I want to thank everyone for joining us today. If you have any questions, please put them into the chat and we will visit about them quickly. If not, you can always stop sharing. Contact us, contact Kate, and she will send you in our direction. And we will help our kiddos in North Dakota get so that we have 80% of our kids proficient. Thanks, guys, for joining us after school. Okay, have a great day.